All right. Hello, everyone. My name is Danny Atallah. I am a physics PhD candidate at Northwestern University working under Fred Razio. I am acutely aware of that I am all that stands between you and a lovely dinner cruise along the river, so I'm going to work with earnest. Let's go ahead and review something here. So there are a few ways to form binaries. One, they can be formed by luck of the draw. Two stars may be bound at birth. You can form binaries dynamically by some dissipative mechanism, namely gravitational wave capture for compact bodies or tidal heating for stars. There's three-body binary formation. Three single stars come in, there is a gravitational catalytic reaction, and you can catalyze the formation of a new binary. Of course, there's also many body binary formation. There's no reason to limit yourself to three bodies, but for the purpose of my work, I'm limiting myself to the simpler case. And a brief history. So early work used a very clever technique called detailed balance. The conclusion is that three-body binary formation was largely negligible, except in the deepest of core collapse. The first scattering investigations concluded the same thing. Now, a little added context here. All of these investigations involved the point mass Newtonian limit only. Now, let's go ahead and fast forward a little bit to 1993 with Kulkarni's early work, to Banerjee 2010's N-body models, to the Morsher CMC runs. It became abundantly clear that mass-segregated black holes are critical to cluster evolution. Specifically, they can reverse core collapse single-handedly through binary black hole formation and the subsequent black hole binary burning, reigniting the core. This reignites interest, no pun intended, in formation prescriptions for Monte Carlo models, because they are, to this day, still reliant on binary formation prescriptions. Now, here's the issue. These prescriptions are overwhelmingly unvalidated. The rate of binary formation, the semi-major and axis and eccentricity distributions, the two bodies which pair, totally educated guesses. This makes us wonder, why don't we try and validate this with scattering experiments? Let's use some previous scattering experiments. Well, the last scattering experiments, the last three unbound body scattering experiments were done by Arseth and Heggie 2 decades before I was born. There has, in case you were wondering, there has been a subtle increase in computing power since the 1970s. And this was all done in the point mass regime. Let's go ahead and move forward here. So how do you throw three bodies at each other? Here's my take. Draw your masses and velocities. For the purpose of this work, I am drawing my velocities from a Maxwellian velocity distribution, all the same velocity distribution. I am going to target a stationary volume with a radius R1. It is convenient to rephrase this radius in terms of chi1 by normalizing the radius of your interaction volume by B90, the strong deflection impact parameter. This also happens to be the typical size of a hard binary. Now, we can draw impact radii uniform in volume. We can isotropically project the position and velocity vectors and then pull our three bodies backwards in time, assuming perfectly straight line trajectories. Now, before you get too skeptical about this, I was able to validate this initial condition scheme alongside a general encounter rate, multi-field encounter rate I derived in Atallah 2024 using a particle in box simulation. And all my 3UB interactions are integrated in Tsunami, of which I am a co-developer on alongside my mentor and collaborator, Alessandro Alberto Trani. Now, we've pulled our bodies backwards. Let's hit play, and if we're lucky, we get something that looks like this. 1, 2, 3. They're coming in, and a new binary is born. It's very simple. This is three-body binary information. In Atallah 2024, I've run 10 to the 10 over 10 trillion scattering experiments. This is one of the largest collections, if not the largest collection of scattering experiments ever done for a single work. all on Quest, Northwestern's supercomputer. Now let's test this, will we? This is a reproduction of Arseth and Hege's money plot. Chi1, this is again, the strong interaction radius. The smaller Chi1 is, the stronger the typical encounter. The y-axis is simply the probability of binary formation. There is very good matching. The X crosses are mine, the gray crosses are Arseth and Hege. This proves that Arseth and Hege's integrator was very good for the time. Now, let's go ahead and look at my updated take here with far greater resolution. A similarity presents itself. There is a very shallow Chi1 to the -2 decay. This encompasses the total probability of binary information given Chi1. The thing is that it is overwhelmingly dominated by very wide, very soft binaries. With my improved setup, I resolve a very critical trend, though. There is a far, far steeper binary formation probability for hard binaries. Combining this probability function with the encounter rate I derived, we actually reproduce Goodman and Hutch prediction in 1993 sans a geometric consideration, of which I'm not going to get into here. Now, had we been using the Arseth and Hege formation rate or the Morsher formation rate, we would have been over-predicting binary formation by a factor of 10 and a factor of 4, respectively, in the equal mass limit. Okay. There we go. Now let's consider substantially large Chi1. So you're considering even weak encounters here. For substantially large Chi1, you begin to recover a trend, namely that there is a scale-free distribution, scale-free with respect to the size of your interaction volume. Binaries with a semi-major axis smaller than your target volume are well described by Jean's thermal distribution, eccentricity distribution, which is a fascinating result for a few reasons I can talk about later. But binaries with a semi-major axis larger than this target volume are well described by a very, very, very super thermal eccentricity distribution. Say that a few times fast. This is really interesting. These are super thermal wide binaries. Does this sound familiar to anyone? The Gaia wide binaries, I think I postulate in my paper that it is possible that Gaia wide binaries are actually well populated by 3-body binaries because the super thermal wide binary is the default outcome for 3-body binary formation. Now, here's a pop quiz. If you are tenured, you will lose your tenure. If you are a postdoc, you will lose your doctorate if you get this wrong, and if you're a PhD student, it's fine. Don't worry about it. Okay, so given 3 masses, M0, M1, M2, M0 is very massive, M1 is medium mass, M2 is very small mass. They're all drawn from the same velocity distribution. Which 2 bodies are most likely to pair? The 2 most massive? The most and least massive? Come on. And we're the 2 least massive. Hold up a finger, 1, 2, or 3. The most massive, the most and least massive, or the 2 least massive bodies. Which is most likely to pair in this scenario? Okay. Come on, I can barely see your fingers, and I have 20/20 vision. Okay. Oh, I'm very annoyed. Some of you may have actually read my paper. Goodness. So if you had picked 1, you're totally wrong. It's actually the 2 least massive bodies. For the past 5 decades, if not more, people have assumed it was number 1 for some reason. And this is the simplest iteration of the 3-body problem. But if you picked number 2, you get a consolation prize because the hard binaries and moderately soft binaries are well described by the pairing of the most massive and least massive bodies. We can talk about reasons for this later, but it's a fascinating result that I love. I can also tell you that the larger the mass ratio, the larger the craziest mass ratio, the lower the total 3-body binary information rate. What this means is that no, an asteroid cannot, a pebble cannot bind your 2 black holes, as opposed to what the classic textbook problem used to say. Now let's go ahead and consider finite size effects for the very first time. A clear trend appears here. The velocity here is, this is the typical velocity of your body as we fix chi1. The probability here is just the probability of binary information. The collision rate is quite a bit more frequent than the hard binary information rate, very quickly. Even for cluster velocities exceeding 3 kilometers per second. But this does not suppress three-body binary information until you have solar mass bodies with a typical velocity exceeding about 30 kilometers per second, which is, so for typical globular cluster cores, you don't get a suppression of three-body binary information. You simply get a lot of potential collisions. Of course, these collisions, you do get a suppression if you're trying to form a binary, which is roughly 100 times the typical size of the bodies which are scattering. Turn on post-Newtonian terms up to 3.5 and tsunami. Same plot. An interesting trend appears here. Post-Newtonian effects do in fact enhance three-body binary information through gravitational wave emission, but it doesn't happen until your typical velocity exceeds 100 kilometers per second. That's pretty big, I know, but it's a useful thing to know. If you have a typical velocity exceeding about 50 kilometers per second, the merger rate does exceed the hard binary formation rate. I do recover the Kinlan and Shapiro prediction of the gravitational wave capture rate, which is great. And come on, there we go. Finite size and post-Newtonian effects don't suppress three-body binary information in globular clusters, as opposed to what may have been previously thought. Now let's combine these two effects. 1 solar mass stars and 10 solar mass black holes. Let's go ahead and scatter them. And what we find is that the rate of collision does in fact far exceed the three-body binary information rate, but here's a similar motif. It does not suppress three-body binary information. That being said, the tidal disruption radius is roughly twice the collision radius, which means that 3UB tidal disruption events should be highly probable. So in codes like CMC or MoCA, where previously you would have formed, three-body binaries with the scattering of black holes and stars, you should actually get a lot of tidal disruption events instead of three-body binary information for those failed three-body binary information calculations. Interesting result. In summary, though, with the next plot, all you need to know here is that hypervelocity stars are in fact possible, only if you're kicking out the lowest mass star, though. It's very rare, but it is possible. Binaries containing a black hole and single black holes do not escape. And now, finally, the world premiere of, I think, the first demonstration of this kind of encounter. These are 3 black holes, 1, 2, 3, and they were unbound, and now I think it's a hierarchical triple. Kozai-Leidov oscillations. And I think we're about to get a gravitational wave merger. No recoil kick because they're equal mass. This is using the RIT prescriptions for merger, the most recent ones, self-consistently in the same frame of reference as the encounter. Summary. Goodman and Hutt 1993 is recovered. It is the preferred old prescription, though it is not totally accurate. Superthermal wide binaries are preferentially formed through three-body binary formation. The unequal mass pairing probabilities favor the least massive bodies in general and the most and least massive bodies for the case of hard binaries. Come on. Finite size and post-Newtonian effects do not suppress three-body binary information. Not directly, at least. And TDEs are highly probable during BH star 3UB encounters. Next steps I am currently working on with my advisor. As you know, Fred Razio is demanding. We are going to be taking CMC initial conditions and trying to get some binary population statistics with a proper treatment of three-body binary information, ahem, tsunami. And hopefully in the not too distant future, if one of you decides to hire me as a postdoc, I will make some semi-analytic prescriptions that properly take into account mass and velocity, unequal masses and velocities in three-body binary formation. Any questions?
All right, we have many questions, so let's start from the front row.
Yeah, thank you, Danny. I put up one finger, even though I knew your work, you know. And this is, I appreciate what you have done, but it's like in many cases, in the real star cluster conditions, what you are also going to do with CMC, things may be different. Yeah. So, for example, not all three masses may have the same Maxwellian velocity distribution. And certainly you are right. I mean, the mass ratio need to be in a certain range. If the third body is a massless body, I am with you.
Yes.
But so I think we should just look at. We have also some data I promised already to share, but I have to look it up. Some pure black hole simulations where we have a huge cloud. There are binaries in the beginning already, and then we have a lot of primordial binaries. And we have a few dozens dynamically formed binaries, and I have already the data to look at this. Yeah, so just see. But really, I think it's good work, and it's important to know these.
Thank you so much.
Boundary conditions, you know, from the clean approach. Yeah, thanks.
Yeah, here. Hey, hi Danny. Thanks. That was really fun. I have a question about this last little simulation you showed. Because so if you first get this eccentric merger, etc. What happens to this final binary? Is that a stable binary? Are they close enough to be in the gravitational wave regime, or?
They are close enough. I actually did not check. I was just enamored by the fact that I formed a hierarchical triple from purely 3 unbound black holes. So I just ran with it. This is extremely rare, and it will only occur in dark clusters with velocity dispersions exceeding something like 500 kilometers per second. So, you know, maybe in the early universe, but so it may just be an intellectual exercise. Actually, it's not intellectual. The computer is doing the thinking. Yeah.
Okay, thanks.
Of course.
One last question there.
Thank you. You mentioned the word lead of Kozai when we're looking in this nice movie. So you really checked it's a lead of Kozai?
No, but it might. I mean, I don't think it's going to be the post-Newtonian precession, specifically because at that ratio, lead of Kozai is probably going to have a stronger effect. That's just my guess, given the same major axis ratios we saw there.
Yes, but the forces between the particles are post-Newtonian. Yes.
Yeah, there are post-Newtonian up to 3.5 is enabled.
So forget about the Kozai.
Okay.
Just try and checking the eccentricity and inclination angle, and you see, but this is not Kozai.
Okay, very cool.
Just with a post-Newtonian, it's suppressive.
I'll check.
All right, let's thank our last speaker. With this, we conclude this session. I guess we're going to see each other on a boat.
Just some announcements about the boat ride.